Dear students, in this short video, we will be talking about applications of Michelson's interferometer. In the previous video, you have learnt in detail about this Michelson's interferometer, that it is an apparatus, an experimental arrangement by which we are able to obtain interference pattern on account of division of amplitude, right? Today we shall discuss some of the applications of this apparatus. The first application is determination of wavelength. Determination of wavelength. Wavelength of what? Wavelength of the source that you are using at the initial place. Now, how do we do that? If you recall the experimental arrangement, you remember that there is a mirror M1 and a mirror M2. This mirror is fixed, its position is fixed, and this mirror is movable. Then we are able to obtain an interference pattern, and which we are able to see through a telescope, right? The fringe pattern is circular. Now, what is the first step in determining the wavelength of the source is that you have to keep these mirrors exactly perpendicular to each other. Focus the fringes through the telescope, they are exactly circular. Now, what you do is that the condition for interference is that 2d cos theta is equal to n lambda. Now, at the center of this telescope, that is at the center of the crosswire of this telescope, you choose to focus any nth bright fringe. Nth bright fringe. Right? Since you are placing it at the center of the crosswire of the telescope, this theta is 0. So cos 0 is 1. We are left with 2d is equal to n lambda only. Now, once you move this mirror M2 slightly towards or away the telescope, towards or away from the telescope, you see that the fringe that you had chosen initially shifts to a next position. It shifts. Initially it was at a central position. Now suppose it has shifted to 5th position, 10th position, 15th position, anything. So n is 15 or n is 10. So what is n? N is the order of the fringe. Therefore, if you want to determine lambda, it can be easily done. It is 2d by n. N is the order of the fringe. That is by how many positions has the initial bright nth fringe shifted once you moved this mirror M2 towards or away from the telescope. Remember, d is the distance, as already told in the previous video, that d is the distance between the mirror M1 and the virtual image M2 dash of the mirror M2. Right? So this is how you determine the wavelength. Now the second important application is to determine the difference in two wavelengths. Difference in two wavelengths. Again, the procedure is the same, that initially you choose to put the two mirrors exactly perpendicular so that the fringe pattern that is obtained and viewed through the telescope is circular, right? The condition of interference is again the same, 2d cos theta equal to n lambda. And since you have placed any nth bright fringe at the center of the crosswire of the telescope, theta is 0, so 2d is equal to n lambda. So we begin with that. So 2d is equal to n lambda 1. Now in the next step, what do? You move this mirror M1 again towards or backwards from this telescope, right? But you do it so carefully that you move the initial fringe, the central fringe, only by one position. That is, in the next step, 2d will be equal to n plus 1 lambda by 2. In this case, you are free to move the fringe through any number of positions unless it is not distinct, right? So unless it is distinct, you can move it through any number of positions until it is not distinctly visible to you. But here you have to be very careful that you have to move this fringe that you had chosen initially at the center of the crosswire only through one position. Therefore, from here you can get n is equal to 2d by lambda 1, and from here you can get n is equal to 2d by lambda 2 minus 1. Then you can equate these two. This is n, this is n. You can equate them. 2d by lambda 1 is equal to 2d by lambda 2 minus 1. And then if you solve the two, what do you get? You get lambda 1 minus lambda 2 is equal to lambda 1 lambda 2 by 2d, right? Now if the two wavelengths are almost identical, that is lambda 1 is equal to lambda 2 is equal to lambda, this is equal to lambda square by 2d. So delta lambda is equal to lambda square by 2d, right? So this is how you determine the difference between the two wavelengths. Now the question is that in the experimental arrangement, we choose a monochromatic light source from which we expect to get a single wavelength. Then what is this kind of an application in which we talk about difference in two wavelengths? This can be so if we use a source of light such as sodium, which actually does emit two wavelengths because it gives you the D1 and D2 lines of the spectrum, corresponding to which the wavelength is 590 nanometer and 596 nanometer, right? This difference in wavelength is indeed very small, and if you want to find this difference, this is the procedure, right? A third important application of Michelson interferometer is to determine the refractive index of a material. Refractive index of a material. How do you do that? You introduce this material in the path of any of the two light beams, the light beams that goes to mirror M1 or the light beam that goes to mirror M2, right? So initially you have a glass plate G1, a glass plate G2. Now you introduce another material of thickness T and refractive index mu, right? Now in the absence of this material of thickness T, what was the path covered by the light? Original path. Original path was simply T, the thickness, right? But what will be the new path once you have introduced this material? It will be mu times T, because I have already told you that optical path is mu times the geometric path. So if the original path is T, the new path will be mu T. So what is the path difference? It is mu T minus T, that is mu minus 1 into T. But we will be multiplying it with a factor of 2 because we know that the ray will initially pass through it and after reflection it will again pass through it. So the total path difference will be actually twice mu minus 1 into T. And it is this factor of twice mu minus 1 into T that you will be equating to n lambda. From here you get that mu is equal to n lambda by 2t plus 1. Again, I'm telling you that this n is the shift in the position of the fringes. When initially you had focused any nth bright fringe at the center of the crosswire of the telescope, and then after the introduction of this material, how many positions did it shift? Did it shift by 15 positions, 20 positions, 100 positions? So that n is the order. By how many positions has that fringe shifted? So this is another important application of Michelson's interferometer.